This is 5.5, Applications of Differential Calculus, Optimization and Kinematics. The objective, students will be able to use differential calculus in order to find largest and least value solutions to real-life problems. All right, so we're going to start with a little investigation together. It says soft drink beverages are often packaged in cylindrical cans made from aluminum. The standard volume of such a can is 330 milliliters. Companies are always interested in minimizing production costs in order to maximize their profits. Are companies using the least amount of aluminum in order to produce the 330 milliliter cans? Let's find out. All right, so your task, really our task, is to find the height and diameter of a 330 milliliter can that will minimize the can's surface area. So number 1 says write down an expression for the surface area A of a cylinder. This expression should contain two variables. So if you think about a cylinder, okay, you know that you're going to have two circles, okay? So that would be 2 of the pi r squareds. Okay, if you unfold the sides, okay, it'll be h high, but what is that distance around? This is where some geometry comes in. That's the circumference, 2 pi r. So look how I did that without having to Google it. Whoops, and there's my h. So the rectangle piece is the circumference of the circle times the height. So the two things we need are the radius and height of the cylinder. Okay? Write down an expression containing the same two variables used in question 1 for the volume. Okay, well, if you hopefully remember this, it's pi r squared h. It says, since the volume of the can is 330, it says we want to equate it, which means set it equal, okay? Now, in number 3, use this expression for V to rewrite expression A so that it only has an R in it. So guess what I'm going to do? I'm going to solve this for H. And this is going to be a common technique we're going to use, okay? So then I'm going to come to the surface area formula, and I'm going to replace H with what we just found here. Okay, so I took my volume, I took my volume and I solved it for H, and that's where I got 330 over pi r squared. Then I went to the surface area and I replaced the H with that. So let's see if we can't tidy this up just a little bit. Okay, the pi's are going to cancel, and one of my r's will cancel, and I can multiply out the 2 times 330, so wouldn't that be 660 over r? Now, something I need to say is r can't be negative because it doesn't make any sense for a cylinder to have a radius that's negative, but also it doesn't make any sense for it to be equal to 0. All right, so now it says differentiate your expression for A with respect to R. Okay, so watch this, and I'm going to rewrite this just a teeny tiny bit. And that R will be to the negative 1 power. Okay, so watch this. We're going to find, and so you may have wondered, why did we do the dy dx? Well, you didn't know what was coming, but I did. And so we're actually going to find the derivative of the area with respect to r. So we write dA dr. So it's 4 pi r minus 660 r to the negative 2. Or in other words, we can rewrite it like this. All right. Now, okay, here's a really, really neat connection to what we just did. If I want to minimize the surface area, I'm looking for a local or relative minimum. How did we do this? We find the turning point here. So I'm going to set it equal to 0. And something I need to tell you about is when you have a fraction, or there's one term that's a fraction, you need to, in order for the differentiation to work, you need to, you might miss something if you bring that over to the other side and cross multiply, because that denominator can do something for me, like it's part of the derivative, so we don't want to get rid of it. So here, that's a cube there. That's a cube. So it's 4 pi r cubed minus 660 because I multiplied by r squared over r squared. All right, so now I'm going to set that numerator equal to 0. So r is about 3.75. Okay, so this is going to be the value for r. And remember, h was 330 over pi r squared. Go ahead and pause and figure out what you get here. And I'm not sure if I can read my own handwriting. I think it's 7.49. So find the surface area. Then you're going to plug that in here. And again, I'm not quite sure I can read my own handwriting. I think I have 264 centimeters squared. So that is the surface area that will minimize, okay? This is the R and the H that will minimize the surface area of the can. All right, so what is optimization? Okay, what is optimization? So optimization in calculus uses mathematical models to provide least value or largest solutions to real life problems. So I hope you found that was actually pretty cool. So you want to find the height and diameter of a 330 milliliter can. That's the volume, okay? That's the volume that would minimize the can's surface area. So number 6 says research actual dimensions and surface area of your favorite beverage. Deduce whether or not companies using the least amount of material in order to have the desired volume of 300 milliliters. So the answers will actually vary depending on which beverage you choose. So number 7 says if companies are using more than the necessary amount of aluminum, give some reasons as to why this might be so. What other considerations might they need to make in the production of the size and shape of the can? So like you will see that sometimes a company is not going to do the minimum surface area because maybe their clientele wants a more sophisticated or something unique about their can or their beverage container. So sometimes you might consider the average hand size of soft drink containers. Like is it children? Is it adults? Maybe you want to consider the stacking size of shelves in a store. Maybe they have to fit something like that. Maybe you need to consider the cost of buying aluminum in bulk. Maybe a company can reduce their cost. All right, just those are a few, and you might be able to come up with some of your own. So I think you're really going to like these optimization problems because we really do get into the real world, and sometimes our stuff is so fabricated that we actually get to see some decent situations. All right, so notice the primary purpose of applied mathematics is to investigate, explain, and solve real-life problems. This process is called mathematical modeling. Here are some strategies for mathematical modeling. If possible, draw a diagram to represent the problem visually. Identify the independent variable or variables and their constraints, the domain. Identify all other constraints on the problem. Translate the real-life problem into a mathematical function or functions. Carry out the mathematics necessary in order to solve the problem. Reflect on the reasonableness of your results, and then apply your methods to other similar problems. All right, let's take a look at example 1. It says, a cardboard box manufacturer makes open boxes by cutting equal squares of length x centimeters from the corners of a rectangular piece of cardboard measuring 15 by 24 centimeters. The sides are then folded up as shown. Find x so that the box is maximized and find the maximum volume of the box. Okay, so let's kind of think about this. My length would be 15 minus 2x. My width would be 25 minus 2x. Let's talk here a moment. You know that x has to be positive, right? We need x to be positive. And if I set this equal to 0, I would get x has to be less than 7.5. Here, x has to be less than 12. Otherwise, you're going to get a negative dimension. So my domain has to be bigger than 0, but because I can't get larger than 7.5 on my length, that's going to be my cutoff there. All right, volume is length times width times height. So the length is 15 minus 2x. My width is 24 minus 2x. And then what's my height? Okay, look at how I folded that up. What would be my height? That'll be x. All right, so let's multiply this out. I got 360 minus 48x minus 30x plus 4x squared. And then I distributed the x. Okay, so now if I want to maximize this, then I want dv, and this would be with respect to x. So it's going to be 360 minus 156x plus 12x squared. Let me set that equal to 0, and it looks like I have a GCF of 12. And I think this will factor. 10 minus x, 3 minus x. So I'm getting x is 3 and x is 10. Now here's why you do a domain, because look, x can't be 10, otherwise that would make 15 minus 20. I'd have a length that's negative, and that doesn't make any sense. Okay, so x equals 3. Now watch this. I'm going to use the second derivative test. Okay, just for practice, okay? So if I do the second derivative, that would be negative 156 plus 24x. When x is 3, if I plug in 3, I got negative 84, which is negative. So V has a local max at x equals 3. So then let's find the volume. All you're going to do is go plug in 3 for x in our volume function. All right, let me pause here, let you find your volume. I got 486, and that's centimeters cubed. So here's my maximum x value. Whoops. And there's your volume. All right, so note, optimization techniques are used throughout industry. Since the goal is to maximize profits, a company's profit is the amount left over after the costs of production have been subtracted from the company's total income. Sometimes it's referred to as revenue. In other words, the profit is the difference between the revenues, the money brought in, minus your costs. So if P of x is the profit, revenue is R of x, and costs are C of x, then you can find the profit by taking revenue minus cost. All right, so let's see how optimization can be used here. It's really quite cool. All right, so a small company manufactures and sells fishing poles. The cost of manufacturing fishing poles can be modeled by C of x equals 7x plus 3, where x is the number of batches, each containing 1,000 poles manufactured. The revenue is modeled by R of x. The company has enough workers to produce a maximum of 1,200 fishing poles. State the domain of both the cost and revenue function. All right, the company can produce a maximum. Okay, so let's kind of take a look here. It says the company has enough workers to produce 1,200 fishing poles. So for my domain, you know you have to do more than one. Now, I'm going to put less than 1.2. Why did I put 1.2 instead of 1,200? Well, x is the number of batches that each have 1,000. So 1,200 would be 1.2. Okay, so that's why I did that. All right, so part B says find the number of fishing poles that the company should manufacture in order to maximize the profits. Okay, well, the first thing we need to do is we need to find the profit function. And we do that by doing revenue minus cost. So x cubed minus 10x squared plus 20x. And I'm going to subtract 7x plus 3. Be super careful here that you did put a grouping symbol around the cost function 7x plus 3. All right, so that's x cubed minus 10x squared. Let's do some mental math. That's 13x minus 3. Now I'm going to find the derivative. Okay, I'm going to find the derivative here. It says 3x squared minus 20x plus 13. All right, this one unfortunately doesn't factor. So what you can do is you can use Desmos or you can use your graphing calculator and go find the zeros or x-intercepts. Okay, so I used my calculator and I got 0.730 and 5.94. All right, so then here's where I can use that second derivative test again. So that is 6x minus 20. So if I go plug this in, I got something that was less than 0. So that's my maximum. If I try the next one, I got something greater than 0. So that's not a maximum. Okay. So then x equals 0.73 is the number of batches to maximize profits. Now, how many fishing poles is that? Okay, how many fishing poles would that be? Well, that would be 730 fishing poles. All right, the company introduces a new process which allows them to produce 6,000 poles. Find the number of poles that would cause the company to minimize profits. So I think we already have that information, right? We have that from right here. So that would be 5.94 or 5,940 fishing poles. We already did the work up above. So the production level that would maximize the losses would be the 5,540 fishing poles. So sometimes, even though you can produce 6,000 poles, like at some point maybe you start losing money. All right, it says by graphing the cost and revenue functions, find the number of poles which would be manufactured if the company is to just break even. That is, the production level at which the costs and the revenue are equal. Okay, so let me kind of make a rough sketch. So what you would do is you would plot the revenue. Okay, plot the revenue. Whoa, I didn't mean to do that. Okay. Okay, so let me change colors here. Okay, so let's say this is about what I'm seeing, and then here was the cost function. So then I'm looking for those two intersection points. So again, you're doing this on the calculator, and I get 0.296 and 1.19. So this means the company will break even at 296 fishing poles and at 1,190 fishing poles. All right, let me kind of talk that one through again because I feel like I did that maybe too quickly. So if you want to do what's called the break-even point, that's where the cost and the revenue functions are equal. So I graphed the cost function and I graphed the revenue function on my graphing calculator, and then there were 2 points of intersection, the 0.296 and the 1.19. So those are the break-even points. All right, it would not maximize the company's profits to produce as many poles as workers are capable of producing. Use your graph to explain why. Well, the company's revenue decrease despite the costs continuing to increase. This may be due to lack of demand for so many poles, which would mean they cannot sell them all. Okay, so the company's revenues decreased despite the costs continuing to increase. This may be due to lack of demand for so many poles, which would mean they cannot sell them all. All right, another area is something called kinematics. And kinematics is the study of movement of objects. A particle moving in a straight line is an example of the simplest type of motion. To describe simple linear motion, you need a starting point, a direction, and a distance. A path is the set of points along which an object travels. The distance traveled by an object is the total length of the path followed by the object after it leaves its starting point. The displacement of an object is the difference between the object's position and a fixed point. This fixed point is sometimes called the origin, and it is not necessarily the same as the object's starting point. All right, so for example, if you run a complete lap around a standard athletic track, the distance you will track is 400 meters. However, after you completed the lap, your displacement will be 0 meters since your initial and end positions are the same. Displacement tells you the shortest distance and direction of the object from its starting point. Displacement can be negative or positive depending on the direction of the object from its starting point. Distance, however, is a scalar quantity which can never be negative, as it only tells you the length of the path the object has traveled. All right, so what does this have to do with calculus? Well, it has a lot to do with calculus. Velocity, we might call the velocity function v of t, is the derivative of the displacement or position function s of t. So v of t equals ds dt or s prime of t. Acceleration is actually the derivative of the velocity function. But if the velocity is the derivative of the position function, then it's the second derivative of the position. This is important right here. When velocity and acceleration have the same sign, an object is speeding up or accelerating. If velocity and acceleration have different signs, the object is slowing down. All right, so these are actually fun to do. So let's look at example 3. A particle moves along a straight line such that its position, s, meters at any time t seconds is given by s of t. Find an expression for the velocity and acceleration. Well, velocity is the derivative of the position function. So that'll be 3t cubed minus 14t plus 11. Easy peasy. Then acceleration is the derivative of the velocity. Whoops, I just caught a little mistake here. Sorry. That should be 3t squared, right? There you go. All right, so then if I want to find the acceleration function, that would be 6t minus 14. All right, part B says find the times at which the particle is at rest. Well, a particle will be at rest when the velocity is 0. Okay, that'll happen when the velocity is 0. So you're going to set 3t squared minus 14t plus 11 equal to 0. All right, so you can do quadratic formula. You can use your graph. I got t is 1 and t is 3.67. I think that actually factored. You could try to factor it. All right, when is the particle speeding up? All right, so here's the deal. I'm going to make a velocity number line, and you've got 0 time, We have 1 is where it rests and 3.67. So what you're going to do is you're actually going to do our test point. And where they're both positive, that's where the object is speeding up. Where they have opposite signs, then the object is slowing down. So, and I am assuming you're okay with the sign charts. If I'm making a poor assumption, please let me know the next time that I see you. All right, so if I plug in 0.5 into the velocity function, I got a positive. If I plug in, say, 2, I got a negative. And if I plug in, say, 4, I got a positive. Okay, so now let me do the acceleration. Okay, so now I'm going to go to the acceleration function. And so, whoops, wait a minute. Sorry about that. Let me do my acceleration. So the acceleration, I need to set the acceleration equal to 0. So t is about 2.33. Because then I need to find where the acceleration is changing sign. So I need to know where that is 0. All right, so let me see. If I go plug into the 6t minus 14, I got a minus and a plus. All right, so they're speeding up. Okay, the particle is speeding up where velocity and acceleration have the same sign. All right, so I'm not sure you can tell on here where that is. Do you see they would both be negative when t is between 1 and 2.33? And then it happens again when t is greater than 3.67. Okay, they speed up when the velocity and acceleration have the same time or same sign. All right, now where do they have opposite signs? Well, they have opposite signs from 0 to 1. And then they have opposite signs from 2.33 to 3.67. So that's where the particle is slowing down. So that you might need to just stop and think, okay? You need to stop and think about that. All right, so that finishes those notes. Then we'll do extra practice together.